at negative infinity. So any initial data you give at t equals to t0 time, t0 time, that's actually consequence of those forces you have applied so far on that particle before that t equals to t0 time.
Okay, I have a question. Isn't gamma a positive number? I mean, T
Yes,
naught, if T naught
yes.
goes to minus infinity, then this minus should make this T naught positive, right?
Actually, I made a mistake then, because no, I wrote like negative gamma. Yeah, it's this gamma thing is positive.
Oh, okay,
Yeah,
okay, okay. Thank you. I get it now.
Yes, yes, gamma has to
you
be
have three
positive
negative signs.
because
You have three negative
for
signs.
stability.
Sorry, I didn't get that.
I told
Like,
that gamma has to be positive for stability actually.
Oh, yes, yes. Gamma has to be positive, yeah. So, like, it's physically impossible to gamma have a negative value, which means instead of like damping out your
Well, in Laplace domain, if gamma is not positive, then the poles are in the right half plane, and it is always unstable.
yeah, mathematically you can say that. Also, physically you can say that if gamma becomes
Negative, it goes up.
that means your system is getting energy from those drag force, which is violating the second law of thermodynamics,
Yeah.
and that's not going to happen. Whatever we have found the correct result, that's satisfying. And now we know how to like find the solution to any arbitrary driving force on a damped harmonic oscillator. So typically this thing is not taught, it's kind of beyond your freshman level physics. It's usually not taught there, I believe. It's at least sophomore level stuff.
And we are at least junior undergrad.
Yeah. So you're supposed to know all these things then, right?
Not everything, but
Mostly. Yeah, this is why like we do not take any like freshman or sophomore student in this course. Like this is just the third session, right? And also like
yeah.
this session is getting already intense, pretty intense. So trust me,
Yeah.
it's going to be hard. Okay, again, I'm saying like take a slot on that term presentation. It's an optional thing for a CNP student, but it's a good experience to do that. But for next term, like next quartile, you have to do it. So
can you give us an idea on which type of topic we can choose?
Yeah, So basically you go to archive.org and you find any research work, any good research work that has been done in previous 10 years, you read it and you make presentation out of it and you present.
Okay.
So it's better to do something that is relevant to your courses that you're taking, but you're not limited to do that.
Thank you.
Okay, how much do we have to explain? I mean, do we have to explain the terminologies also
No,
using
no, 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 no.
or the
So,
word only?
yeah, like what about what the researchers have done in that work? So that's you have to explain. So it's not for like yeah, there are a lot of students, those are like freshmen or sophomore will be present in that presentation, but it's not meant for them actually. So you do not need to explain everything. You just need to explain the basic thing, like the basic outcome or the findings they have.
Okay.
And again, it's the time zone is written over there. That is UTC +6. That means Bangladesh time actually. And it's going to be on Saturdays. On Saturdays, so for other people's presentation, you can like be there to support them, to ask them questions. And if you are looking into this schedule, then you see like some lines are like gray marked and some are white. For white, those are like mandatory for those whose name appear on a like white line. That's a mandatory for them. But if your name is on a gray marked line, then it's optional for you. Okay, we have 2 more minutes.
Will there be any question answer session in the presentation?
Yes, so the time limit is for the presenting is actually 10 minutes. So you can take up to 15 minutes, but 5 minutes is there for a question
answer session. Yeah, thank you.
So you can see like everyone is given a 20-minute window.
Yeah.
So that's all. Like try to be limited in a 10-minute slot. That would be better. So if you make presentation, just make 10 slides, not more than that.
Oh, okay. Thank you.
Okay, it's already 10:35 in my clock, so we can start. Okay, let's clean the whiteboard. Okay. So now we are going to dive into Lagrangian mechanics. basically classical mechanics is a theory of dynamics. Like it's a general theory of how things move. So by things we mean a lot of stuff. So it could be a particle, it could be a collection of particle, it could be a rigid object, it could be fluid, it could be field, like abstract field, like electric field, magnetic field. So basically the motion, like when we talk about motion or dynamics in principle, in general, so that word dynamics of something, that something is actually pretty much broad. It's not limited to only particles only. So let's have some example, and then so consider you have a point mass, so it can move in three-dimensional space. So you draw a coordinate and you find it, like you apply Newton's law and you find the trajectory of it. So it could be two particle, like you have a coordinate set up over there and they're gravitationally attracting two particles and they're probably moving like this and probably they're orbiting each other. So that's a system of particle. It could be a rigid body, like a heavy top, could be a heavy top like that, spinning top that's spin like the earth itself. So that's also dynamics. So it could be fluid, like it's hard to draw fluid. So basically when we're drawing, when we're talking about fluid, the motion is happening for each of the points. So you can, in your imagination, you can consider this kind of thing like millions particles actually floating around. So that's what fluid is really. It could be a solid itself, like in general, it could be like a piece of iron. So it has also a motion inside of it, like if you press or if you squeeze it, it responds to it. Like if you apply force, it responds to it. If you like give it a flick, then it propagates wave motion inside of it. So that's also dynamics. It could be in principle like electric fields. So you wiggle a point charge Q over here, and electric fields that is generated by this point charge probably at a particular point, like this point, that electric field changes with time. So all of these are pretty general thing that is described by general word dynamics, right? So when we talk about Newtonian mechanics or Newtonian dynamics, that particularly talks about a motion of a point particle or system of particles. Or particularly when we talk about mechanics, it usually means we are talking about objects, not fields, like that you can touch actually, like fluid is also object here. But the analysis of motion, analysis of dynamics is pretty general. Like Maxwell's equation, it's also a theory of, it's a theory of dynamics. It's a theory of electrodynamics actually, how electric and magnetic field moves in time. So all these kind of ideas of dynamics can be generalized or simplified or like reduced down to one single idea, one single intuitive and great idea, that is a defined quantity action, we call it by S. Any motion that happens in time that always tries to make that action to be stationary. So this is the one single equation that governs all of this. So any motion, like or any theory in physics actually can be generalized, like can be reformulated to write in this form. So that's why it's so important to us. So Lagrangian mechanics is a particular part that we are going to talk about. Like that's all about mechanics only, like theory of moving objects, but it could be generalized into more generic things, the general things like electric field, magnetic field, gravitational field, and so on. Do you have any questions so far?
I have a question.
Sure.
Actually, I did not understand that del S equals to 0 and its physical significance.
You need not to understand. We just call it action. We'll define it later. So right now you need not to, just understand that there exists some quantity for every system that is extremized for the motion of that system.
I think one or two example would be better for me to understand.
Yeah. Okay. So that one example we are going to discuss, that is basically Lagrangian mechanics. Any other question? Okay, let's start. We'll understand actually. We will understand this equation bit by bit. You may not understand it just one day, but it will be clear over time. Okay, so in classical mechanics, we have our Newton's law, like total applied force on a particle. Actually, we'll write like that. Say you have a system of particles, 1, 2, 3, 4, 5, 6, 7, 8, like that. You call one of those particles like your ith particle. So you have n number of particles and you label them. This is your first one, this is your second one, and so on. And you pick up a typical one, you call it ith particle. That means you labeling this thing with I. Its position vector that you use to describe this particle's position, we call it Ri. And derivative of Ri gives you the corresponding velocity and momentum. So velocity of that particle at a particular time t would be dri over dt, right? And the acceleration of that particle would be ai at some time t would be d2ri over dt squared. But that acceleration is caused by something, right?
Yeah.
Something is giving it a force. Say that force is Fi. So Fi total is the total amount of force that is being applied on particle I. So by Newton's law, we know Fi total equals to Mi, where Mi is the mass of that particle,
into ai.
multiplied ai, right? So this is what our Newton's law tells, right?
Yeah.
So now, say you have your you could have actually two kind of forces in your system. Two kind means one kind of force that does something and another kind of force that doesn't do anything. So what do I mean by that? So let's say you have a pendulum. So what forces are acting on that?
Tension, force, gravity.
Okay, one is tension, another is gravity.
Yeah.
What else? So these two are actually, right?
Yeah. But we can resolute and see that only the tension force is actually
Yeah, we can actually resolve these forces in polar coordinate. Actually, we set up a polar coordinates considering this point as an origin, and we can see that that this length is fixed, so this particle cannot go out of that particular circle, right? So it goes in a circular motion. So So when you resolve your motion in two components, like one is tangent to that circle and another is perpendicular to the circle, that perpendicular motion of that particle that is perpendicular to that circle, that motion is actually restricted by this tension force.
Yeah.
And another thing, like the other part, that actually gives the dynamics of the particle, like it moves this way and that way, right? So you have two kind of force. One is actually doing something that is mg over here, actually some part of mg, and another is t and some another part of mg that's are actually canceling each other. So these two kind of forces, so one is always unpaired and another is paired. So the paired one, we call it constraint force.
Constraint force.
And another is unpaired one, we call it applied force.
Applied force.
So constraint force, that actually gives the constraint that it makes the particle move in a particular way. It that motion is always perpendicular to that constraint force. Like here you can see that tangent force is perpendicular to the motion direction of the motion. So in principle, all we need to worry about these unpaired forces, because these paired forces, these constraint forces, they always appear in pair. So they always cancel.
They vanishes. Yeah.
Yeah, it vanishes. Like this T is always cancelled out by some part of mg. So those part of mg, that specific part of mg and that T, those are paired ones, that's constraint forces. And we have the rest part, that is component of mg in this direction, that is unpaired one, and that we call the applied force.
But
So,
if constraint force is velocity dependent, then I think it won't be paired. If the constraint force is velocity dependent, then generalized velocity dependent, then it won't be paired, right? For example, friction force.
yes, but we are talking about like constrained by this coordinate constraint. That means you can fix a coordinate. For the situation you're talking about, like velocity dependent one, then you cannot actually give a constraint over there. So that's a problem. So when we are talking about constraint here, remember, it's actually not slowing down the particle, or it's actually doing nothing.
Yeah.
So frictional force is not a constraint one. It's an applied force. It's a real one in this context.
Okay.
Okay, so we can resolve our forces, like total force, in two parts. One is applied one, that is we call it Fi, and another is constrained one, we call it this. Right?
Yeah.
So now, in general, your pendulum, like let's erase this thing and redraw this thing. In principle, your pendulum could have a displacement like that. In principle, because it's actually sharing this xy plane. So on xy plane, infinitesimal change in position is actually dx x hat plus dy y hat, and that's an arbitrary direction. It doesn't need to be in the direction of the actual motion, right?
Yeah.
But we know that even on xy plane, when we have a constraint system like this pendulum, it cannot go in any direction. It has to be on a particular track or trajectory.
Yeah.
Phi direction.
So yeah, here particularly
Here
in
is
this
the
part.
sphere.
So this dr is pretty general, right? Infinitesimal change in position, this is pretty general. But out of that whole generality, we pick out a class of change of position. We write it like that. We call it a generalized displacement or virtual displacement. And that virtual displacement is actually the displacement that particle can take in reality. So yeah, you could say it's a misnomer. Yeah, I agree with you. So this is actually, this delta R is actually more real than this dr. But there is a reason that why we call it virtual. So delta R, this virtual displacement, it's a displacement of the system, that actually consistent with the constraint force. So if you consider like a displacement that moves in this direction, that's not consistent with the constraint, that actually moves out of this curve, and that's not consistent with your constraint force. So by consistent means the specific path that a particle has to follow when your constraint force is like constraining that particle is to move in that track. And on that specific track, a displacement is called, an arbitrary displacement on this track is called a virtual displacement. I think,
I have a question.
just give me a moment. So actually I can give a better example, then you'll see what actually I'm talking about, why we need to separate that. Say you have a system where you have a cylinder, a hollow cylinder like that. Oops, of radius A, and another hollow cylinder of radius B, and they are concentric. That means they have same coaxial, basically, not concentric, they're coaxial, so they have same axis. So this small gap, this thing is always A minus B, right?
Yeah.
So, and you can see that has a like cylindrical shape, that A minus B, right? This gap. Now, let's say you have a marble, a ball, small ball that has a diameter of A minus B, and you just place it inside of that thing and say it's totally frictionless and it can move. So in principle, it can move this way, that way, like in other way, like but it always needs to be, the motion needs to be the tangent of this cylinder, right? Like tangent to the surface of this cylinder. I'm bad at drawing, but
Yeah, I can understand.
so let's draw in another way. So this, so basically you can consider you have just a cylinder and your particle is actually has to move on the surface of the cylinder. So it can move this way, this way, this way, but always it needs to be on the surface. So in a particular applied force situation, probably it will follow this trajectory. Or when you change the force, probably it will follow another trajectory like that. But whatever the trajectory is, infinitesimal displacement of that particle, any arbitrary infinitesimal displacement, that has to be tangent to the surface. That's the point. So in reality, when you're seeing the motion, in reality your particle may not follow this specific path. But when you are talking about virtual displacement, that's an arbitrary path that actually particle can follow. It may not, but it can.
Yeah.
So, okay. I think everyone now on the same page, right? We all understand that.
Yeah.
Okay, so someone had a question. I think Jaber had a question.
Yeah, right. So if we consider the above example, here we can see that the particle is moving on a circular track, but basically where it can go, it is basically sphere, the whole domain.
Yes.
So any tangent vector on that sphere can be a virtual displacement, right?
Yes, for a pendulum, yeah.
Okay.
Yes.
Yeah.
An arbitrary displacement on that sphere, which is tangent to that sphere, is a virtual displacement. It's an arbitrary, like it's a typical displacement. Like your particle in reality may not follow that specific path, may not follow that specific displacement, but it can always, for a given initial condition and initial like applied force, it can follow that path. That's what necessary. Like here, going above the surface is out of question. Your particle cannot go out of that surface because of constraint force.
Yeah.
So now we understand that constraint force and virtual displacement of that particle, we call it delta Ri, has a particular relation, which is that what would be the dot product between those two?
Zero.
It has to be 0. Do you guys see it? Because to make the particle move on this surface, that force that is actually making this particle moving on this surface, so that has to be applied on such a way that actually that is perpendicular to this surface, otherwise it won't work. So if some component of that force is tangent to this surface, that particle will follow that way. So constraint force that is actually holding that particle, that those have to be like perpendicular to the constraint surface. So that's why we have this relation. Do you guys agree?
Can you explain this one more time?
Which part?
Yeah, this one only, the F dot delta R equals to 0. Yeah.
Because our constraint force that is actually making that particle move on that cylindrical surface, they are actually perpendicular, right? Perpendicular to the surface. Because those are holding this. So you want to hold something like on a specific position, you push on both sides and you make it move on a specific path. So that's what those forces are doing. So those are perpendicular to the surface, and this delta Ri, the virtual displacement, that is tangent to the surface. So this thing should be satisfied, right?
Okay. Yeah.
Okay. So now, if we take dot product of delta Ri on this equation, what we get? So Fi dot delta Ri plus Fi constraint dot delta Ri equals to MAI dot delta Ri, right? You can write like that.
Yeah.
Okay. And we can see that this term actually is 0, right?
Yeah.
So we can write like this: Fi dot delta Ri equals to MAI dot delta Ri, and we can take this thing on the opposite side of the equation and take a sum over it. So we can write like this: sum over I equals to how many particles you have, 1 up to n. So if I minus MAI dot delta Ri, this has to be equals to 0, right? According to Newton's law.
Yeah.
So whenever you want to solve a equation or solve a motion of a system, you can just start with this equation instead of F equal ma, right? And you actually need not to
D'Alembert
worry
equation.
yeah, this is D'Alembert's principle, we call it. We call it D'Alembert's principle. Now, in this expression, you need not to worry about the constraint force anymore. Only you worry about the applied forces. But in Newton's law, you had to consider those constraint forces. Now you do not need to. Okay? So this is actually an equivalent equation for of Newton's law. You can start your writing down this and solve your equation of motion. So now we are going to use this D'Alembert's principle to derive a new equation of motion that is not particularly like this Cartesian looking. We want our coordinates to be absolutely general, like we want to be switching from Cartesian to polar to be like elliptical, ellipsoidal, any coordinate we want. Hyperboloidal or any coordinate we want. So we want our coordinates to be absolutely general. We do not want to fix our attention into a specific kind of coordinates. So we perform a coordinate transformation. Coordinate transformation of Ri that actually Ri, you can write this Ri in terms of your new coordinates. Those are, we call it Qs, like Q1, Q2, up to, say you need n number of terms. If you do not have any constraint, just it's a free three-dimensional space, then actually each position vector has 3 components, and if you have n number of particles, then it's thrice n Qs you need. That means small n will be thrice n. But if you have m number of constraint number is m, then those amounts are reduced from this. So now small n doesn't need all those coordinates. Like for pendulum, if your pendulum is restricted to xy plane, then you have 2-dimensional coordinate system. But do you need 2-dimensional coordinate system to explain a pendulum? No, you can actually use 1-dimensional system because it's always r equals to some fixed value. So only change that the value is changing, only coordinate that is changing, that is phi only. So for here, for a pendulum, your big N, your what's actually, I shouldn't call it big N. Your unconstrained system has 2 dimension of 2, and your constrained system has a dimension of 1. Or you could consider actually.
Are we talking about translation and motion only?
Yes. Where?
In the perspective.
Yes, only translation. Yeah.
Thank you.
Like not a rigid translation actually. That's what you need to understand. It's not a rigid translation. It's a translation, but it's an arbitrary generalized translation. That's why we use this transformation. So say you have your pendulum attached to this thing, and it can actually, in principle, it can go around a circle as well. Like it can move on a part of a sphere, right? So here you have 1-dimensional system, like one particle, and the total dimension your space is allowed is 3. So 3 multiplied by 1 would be your big N in general. But now you have your constraint number, that is L, R equals to L, and that is one constraint, right? So you need to, like number of coordinates you need is 3 minus 1 equals to 2. And that's obvious because you need two angles, like one is theta, another is phi, to express position of that pendulum, right? When it's moving on a conical or any arbitrary trajectory. It's not a plane pendulum.
Yeah.
When we talk about plane pendulum, we are actually imposing another constraint that say x has to be fixed. So this is another constraint equation. Now instead of having one constraint, we have now two constraints, and our degrees of freedom is 3 minus 2 equals to 1, which is the usual plane pendulum has like only one coordinate, that is phi. So we are talking like that. Is it understandable at this point?
Yeah.
Okay. Also, we could do a little bit trick. We could choose our coordinates transformation coordinate system transformation to be time dependent as well. It could, in principle, depend on time. Later, we will see kind of coordinate transformation; those are time dependent. So you could write a relation like your Q1 equals to like x squared plus twice y plus z plus t. Say it's obviously a time dependent transformation. So like that.
I have a little confusion. I understood the little n, which indicates that the number of coordinate I can use, but I am confused about the capital N.
Oh, capital N is like the number of particle you have.
Okay, so why I have written the number of particle to be 3, where one single particle is...
No. Thrice n is in 3 dimension. Actually, I should write n equals to d multiplied by n minus m, where d is the dimension of the space-time.
Oh.
Dimension of the space.
Okay, and the meaning of m.
Which the meaning of m? This.
M. Yes.
Yeah, this is the number of constraint you have in your system.
Okay.
Like number of equation that tells that your coordinate has to be restricted like this. Say that for a pendulum, your position, like your coordinate r, like the distance from your particle to the center.
This is fixed.
It is fixed. So that's one equation, right? L equals to r.
Yes, one
So
equation.
in this particular case, your m would be m equals to 1.
Okay, now I understood.
So now rest of the things that are actually cannot be constrained, or those are not constrained, that can be vary actually in time. So Ri is a function. Ri is a function of those. So actually it's better to write in other way. Usually we write it as like this: Qi, that means any of the coordinate, is a function of Ri and t, like that.
Okay.
So now take the velocity of it. So what would be the velocity of ith particle? That would be dri over dt.
Yeah. Chain rule.
Yeah, according to chain rule. So, and that would be, according to chain rule, that would be delta Ri over delta Qj, dQj, or actually dQj over dt, sum over j, where j equals to 1 up to n, plus the last one, delta Ri over delta t, according to chain rule, right?
Yeah.
So this is our velocity. So now for that, to use the DLMR's principle, we need several things. We need our acceleration. We need our delta Ri. So let's take those. So delta Ri, that means variation of Ri, equals to, according to chain rule, delta Ri by delta Qj, variation of Qj, sum over j, like that.
Yeah.
So you might argue that why don't we have like this thing here, like delta Ri over delta T, variation of T. So there is the reason actually. Variation, this operation, we just talked it about implicitly, but it has a rigorous mathematical definition, and we'll see that later. And that due to that definition, actually, that variation of T, that's actually cannot take place. Like variation of T is by default 0. You cannot vary that time. Why? I'll explain it. You cannot vary a number. You can vary a
Time independence.
No, not due to time independence. Here T is a parameter, that's why. Oh, we'll explain that later. We'll explain that later.
Okay.
Simply you cannot write that. Actually, just after completing this, we'll study calculus of variation and we'll see what this curly delta mean. Okay, so now we have an expression for delta Ri. So what happens if we do a dot product with fi dot delta Ri, because we need that, and take sum over I. That gives us sum over j, sum over I, delta Ri by delta Qj dot fi multiplied by variation Qj, right? We can call it, this whole thing as some sort of work, right?
Yeah.
So now this thing is a work, and this thing is a displacement on the space of those Qs. We call it configuration space. That's a displacement of configuration space. Then what this thing?
Work in this. No.
Look, compare with this expression. So we have a work, infinitesimal work. We have infinite
force type thing.
Yes. So this is a kind of force. This sum is a kind of force. We call it Qj, a generalized force. In principle, generalized forces are not. In principle, those forces, those do not have that mass multiplied by acceleration square dimension. It could be like torque. Torque is a force as well, right? But in different kind of coordinate. So these are those. So we call this thing as generalized coordinate, generalized forces. Forces, and obviously Q is called generalized coordinates. And this thing is called virtual work. Remember, this variation Ri, it's not the actual displacement that particle takes, but it's a possible displacement that particle can take. So this work is not a real work that actually is done on the particle, but this is a possible work that can be done on the particle.
Yeah.
Okay. So now we have dealt one part. Like we had two parts, right? One is Fi dot delta Ri, sum over that, and then MAI dot delta Ri and sum over that. That part we have to deal with now. So let's simplify it. Like now let's deal this part, MAI dot delta Ri and summed over I. So we have an expression for delta Ri, but do we have an expression for AI in terms of Qs? We have an expression of delta Ri in terms of Qj's, but do we have an expression for MAI in terms of Qj's? Do we? Have we derived it yet? No. We only derived velocity, and velocity was sum over j equals to 1 up to n delta Ri over delta Qj we call it Qj dot. So dQj over dt we call it Qj dot for simplicity, plus delta Ri over delta, like that. So now if you take second order derivative, second order time derivative of this thing, you get acceleration, right? So take second order derivative. AI would be dVi over dt, and that is by chain rule according to the previous one, Vi sum over k delta Vi over delta Qk plus delta Vi over delta T, like that. Oh, I missed
Qk dot.
something. Qk dot, yeah. Now what happens if you substitute your Vi over there? So you have your sum over k delta delta Qk, and then your Vi, which is this sum over j equals to 1 up to n delta Ri over delta Qj dot plus delta Ri by delta T. And then also you have your partial derivative with respect to time, that is delta delta T of this whole thing again, sum over j equals to 1 up to n delta Ri by delta Qj dot plus delta Ri by delta T. Okay?
Yeah.
Happy? So far? Okay. So
Yeah.
now take derivative. Take derivative. So what do we get? Actually, we can do it in another way, and that would be better, I think. Okay, just write it down. The a.
When
We
j
have an
not
expression
equal
for
to k,
a.
I think.
Now. J is not equal to k,
Then I think.
No, it doesn't reduce.
Minute. Well, yeah.
No, it doesn't reduce. So let's start with this thing. So Vi dot delta Ri. You can do that. right? And what if we take DDT of that? By product rule, we get VI dot delta RI plus VI dot variation of RI dot. You can write that. Can't we? Hello?
Yeah. We can.
So there is a thing. I have switched the order of time derivative and variation, and we can easily show that those are actually compatible. Like those can be done, one can be done earlier than another. If you want the proof, I can just quickly prove it, or you can believe it. So those are actually switchable. How? Look, if you have your DDT of some variation of Ri, that is delta Ri over delta Qj, variation Qj, sum over J, then you can actually first expand this DDT. So by expanding DDT, you have like qk dot partial derivative with respect to qk plus delta delta t. Now these two things, like derivative with respect to q and derivative with respect to t, those are partial derivative, and this thing is also a partial derivative, right?
Yeah.
And that you can switch. That you can switch. So again, you just like collect those terms, those are similar terms, then you're done actually. Okay, if you need it, then I can show it as well. So it gives you qk dot and delta delta qk delta delta qj ri. So switch the derivative order. So I do the k order derivative, k derivative first and j derivative then multiplied by variation of qj. This is one term. Then plus what else do you have? You have time derivatives. So you have your delta delta qj partial derivative with respect to time. And the rest part, you could say that why not you take derivative of variation of that thing. You take that and like I can show one term. So derivative of this partial derivative, so it gives you delta qj over delta qk, that's a and variation of that thing, that gives you Kronecker delta jk, and this is a constant thing, so when you vary this thing, it gives you 0. So you need not to worry about the other part. And recollecting these terms, so like switch here, also switch the order of t, so it gives you like this thing. Did I write it correctly? No, it should be j and then variation qj. So I'm collecting this thing, we can actually write this is basically a variation of r dot ri dot. So yes, those are switchable. So now actually we need this part, right? We needed this part. So ai dot delta ri equals to ddt of vi dot delta ri minus